Last time we started section 2.3 and we looked at the product rule. And we found out that the product rule is unfortunately not as friendly as we maybe had hoped that it might be. And then we started talking a little bit about the quotient rule, just a touch, and we talked about, and I already spoiled the hope that you had in your heart that the quotient rule might actually work as well in a very fun and friendly and easy way. I told you that it wasn't going to. So we're going to actually see that it doesn't work with an example much like we did on the last one for the product rule. So we're going to actually use the same or similar functions that we did when we talked about the product rule. And we're basically going to decide if the order matters, whether we do the division first and then do the derivative, or if we do the derivatives first and then the division. So in other words, are these sort of commutative operations? And so we're going to take f of x, which is 4x to the 9th, divided by g of x, which is x cubed, and we're first going to divide them, and then we're going to differentiate. So if I divide 4x to the 9th by x cubed, what do I have? 4x to the 6th. Yeah, remember you subtract exponents with the properties of exponents. And then we're going to take the derivative of this. So what's the derivative of 4x to the 6th? 24x to the 5th. Okay, now that's really the derivative of this thing. I mean, if we're trying to find the quotient, the question is whether or not we could have done it in the other order. Okay, so this is definitely the derivative of the quotient. So if I took the derivatives individually and then I did the quotient, will I get the same thing? That's what we're going to explore. And well, yeah, we've already spoiled it and told us that it's not going to work, but let's actually see it not work. All right, so what's the derivative of 4x to the 9th? 36x to the 8th over what? 3x squared. Okay, what does this give me? 12x to the 6th. And the spoiler that I mentioned last time, of course, is that these are not the same. So the order does matter. We can't just take the derivative of the top, the derivative of the bottom. There is something else that must be done when we're doing a quotient rule. So just like the product rule, we have a different form for what the quotient rule actually is. And this is it. And what you'll notice in the numerator of the quotient, it is very similar to the product rule. What's different?
G of x comes first. F minus.
There's subtraction. It's in a different order than I expressed it when I did my version of the product rule, but the real difference is that it's subtracted in the middle instead of added. So the numerator is much like the product rule with subtraction instead. And then you see the denominator is just the original denominator squared. Okay?
Is that just the prime thing?
Yes, those primes are derivatives. So those accent mark kind of things, those are the derivative notations. So you're going to take g of x times the derivative of f of x minus f of x times the derivative of g of x. And would you like a mnemonic device to help you remember this one?
Sure.
Sure. Okay. So I'm going to teach it to you the way that it was taught to me when I first took calculus. It's the one I always think of. And we'll see if you know the television show that the language comes out of. Because this speaks to my age. Because I don't know if you're going to know it or not. And there will come a day when people won't know it. And I will feel very old. And today might be that day. So we're just going to see. All right. So we're going to call what's on top high. And we could call what's on bottom low, and that would be okay. But we're not. We're going to call it like Santa Claus ho. Okay, ho ho. Okay. High over ho. All right. So the derivative, when we do this, is ho-de high minus high-de ho all over ho ho. This is what I say in my mind every time I do a quotient rule. Ho-de high minus high-de ho over ho ho. Is that what they taught you? I know people who will do it high over low, and obviously that sort of looks friendlier. But do you know what portion of this comes from a television show that might be older than you? Heidi Ho. Do you know what it comes from? Nope, it's not hee-haw. That's before my time, too, actually. But thank you for thinking I'm very old. I appreciate that today.
My Little Pony.
No, it is not My Little Pony. Oh, my word.
What type
Like the
of show
Muppet
is
Show
it?
or something.
It has real people in it. It's not a cartoon. It was a sitcom.
Well, Seinfeld.
No,
CSI.
no. Today is officially the day. You guys are my first class that hasn't known. Oh my word. It's officially old. It was called Tim the Toolman Taylor was the show part, but it was I don't know, Tool Time. Tool Time, Tim the Toolman Taylor. I don't know. But that's Home Improvement. No.
Yeah, that's it.
Is that what it's called? Was it called Home Improvement? Okay.
Yeah.
Yes.
Oh, and he has like.
And the neighbor says, "Heidi ho,
Yeah, and you
Heidi
can only
ho,"
see
and you can only see the top of his
Okay,
face.
so you're not old.
I'm not old. Oh well, thank you, Luke. I appreciate that. You guys are so encouraging today. Okay. All right. So this is a mnemonic device for helping you to remember it. Thank you so much, Minnie. I appreciate it. All right. So we're gonna do some of these now. We're gonna practice. Okay, you guys ready? Here's our first one. Now, it is sort of wise to take a look at the quotient that you have, because we have seen some quotients where we were able to actually simplify what we had. Do you remember that? Like the numerator had some addition and subtraction, the denominator didn't. We can kind of divide the pieces out. So if that were possible, we could, sort of avoid the quotient rule. We can't do that on this one, and the reason we can't is because there's addition or subtraction, in this case subtraction, in the denominator. That subtraction in the denominator forces me to have to do something different, okay? So just kind of making you aware of the fact that we really can't do this with any of the other methods we've discovered before. So this Hody High says ho. I'm going to write down the first thing is the denominator, what's on bottom. 5t minus 3. And then d high means the derivative of what's on high, the derivative of the top. So what's the derivative of what's on top? 2t and then minus 0, right? It's just 2t. Is everybody good so far? I'm not writing the apostrophes because I'm actually taking the derivatives as I'm going. So yeah, this is what I'm trying to do. I'm trying to write down, I'll write down the real version of it, if you will.
Okay.
So if this is f of x and this is g of x,
Yeah.
then, it's an f, then I did the denominator,
Yeah.
and then I did the derivative of the numerator. And the derivative of this numerator is just 2x
Okay.
over 2t. Sorry, we're working with t's. And then we're going to do it in the other order. We're going to do the numerator, and then the derivative of the denominator. And then we'll put the denominator squared here in a moment. Okay, so this is subtraction. Something sometimes people forget is it's subtraction instead of addition. And we're going to reverse the ordering. So now I need the numerator, which was t squared minus 4, times the derivative of the denominator. What's the derivative of this denominator?
Is it plus 4 or is it be 5?
It's plus 4, thank you. I subtracted instead. It is 5, right? The derivative of the numerator, or of the denominator, excuse me, is just 5. And then we write this on top of the denominator squared. If you're doing this on the gateway next week, you would stop right here. You wouldn't do any simplification, right? You're not doing it on the gateway today. You're working through this to simplify. Generally speaking, the denominator can stay as is. There's very, very few and far between. I can't even think of any reason why you would ever really want to multiply that denominator out. Okay? You might be able to factor the denominator with something in the numerator when we're done even. If you leave it in factored form, it's a possibility. We're not going to be able to on this one, and in most cases you can't. But occasionally you might be able to. But it doesn't get any cleaner or simpler or nicer to multiply that denominator out. It just gets messier, right? So we definitely are not interested in messier. The numerator, however, will get cleaner and nicer and simpler if we multiply it out. And the reason is because we'll be able to combine some like terms if we do. So we're going to do that. So we're going to distribute the numerator, first piece. So I'm going to have 10t squared minus 6t. And then on the denominator, I'm going to multiply the 5 through, and there's a negative as well, so both of my pieces are going to change signs. So I'm going to have negative 5t squared and negative 20 all over 5t minus 3 squared. Yes, Dawson?
Before you did all that,
Mm-hmm.
could you not like, in 5t minus 3 squared, could you put it into 2 and then cancel out the...
The only way the 5t minus 3 in the denominator will cancel the numerator is if every piece that's multiplied has it in it. So like you see the 5t minus 3 here in this piece, but there's no 5t minus 3 here.
So,
So you can't cancel it.
okay.
That's a good question. I was going to mention it as well. Because sometimes I do have people that try to cancel that, and you can't do that. That's like taking, for example, and I know you guys wouldn't do this in general, but that's like taking x squared minus x plus 7 and dividing by x and doing this. I'll just take it out of there. I can't do that, right? If I'm going to take it out, I've got to take it out of every piece of the numerator, and I can't on that one. So we're not able to do that, right? Okay. Numerator cleans up just a touch more. What can you do? Yep, that's 5t squared. And then minus 6t and minus 20 over 5t minus 3 squared. Now, if the numerator factored, and it factored into a piece that was the exact same as the denominator, we would want to factor the numerator. It cannot possibly factor into what the denominator is. Do you know why? Do you know why, Gus? Yes, that's exactly right. I can't take this 20 and change it so that I have, like if I were to try, I would want to have a 5t minus 3. The only way I can get that, certainly the 5t is possible, right? I would have that. But I can't break 20 down into a factor of 3 and a factor of something else. Are you guys with me? So if it doesn't have that feature, then there's no point in factoring the numerator. We might do so at some other point in the future for some other reason, but for the purposes of simplification, there's no point. You guys with me? Okay. So it is very wise for us to look at that, though, because if it had that possibility, we would want to do it. It just doesn't work on this one.
Wait, why would you do minus 3?
If it had the ability to be a factor of 5t minus 3, I would want to, because then it would reduce with the denominator. Minnie?
Do you want that, leave this down, do you want to factor
We
it?
don't need to factor it because the only point in factoring it would be to simplify it with the denominator.
Okay.
So we're not going to factor it. But there will come a point when we will factor it for another reason, but we're like a chapter away from that. Okay, so we're not going to do that later. Yes. Yes, we'll be finding some other things. Okay, another one. This one's actually cleaner because I don't have polynomials everywhere. This one, again, has the ability to be worked through with a quotient. I can't simplify it in any way to use any of my basic derivative rules from 5.2, or sorry, from 2.2. So we're going to do Hody High, the denominator, times the derivative of the numerator. So what's the derivative of sine x?
Cosine.
Good. Derivative of sine is cosine. And then we have subtraction. And then I want to do the numerator, that's sine of x. And the derivative of the denominator. So what's the derivative of the denominator? 2 or 3? 3x squared. And this is supposed to be over what? X cubed squared, which will simplify to x to the 6 in a sec, yeah. Okay, so this is sort of the nuts and bolts of what we would write down for the gateway. You could stop there. But this one will simplify, and the reason it will is because I have an x to a power in every term. And a term means things that are multiplied together. So this is all one term. This is all one term because it's all multiplied, each of those pieces. So I have an x to a power in every term. I'm going to do one step before I actually start reducing things, okay? I'm going to just clean them up a little bit. So I'm going to x cubed cosine x. I'm going to move the 3x squared to the front just because I like to see it there better, not because it has to be there. This 3x squared sine of x. And then you guys told me just a moment ago with rules of exponents, this should be x to the 6th. Not the 5th, but the 6th. An exponent to an exponent is multiplied. Okay, now how many x's can I reduce? 2. because every piece has at least two x's in it, right? An x squared in it is what I mean.
Yes.
So the first one, if I reduce it by a power of x squared, or by a factor of x squared, what will the x cubed become? X. I still have the cosine x, okay? And the x inside of that's an angle, so we're not messing with that x.
Okay.
And then I've got 3x squared, and if I reduce that by a factor of x squared, what do I get? A 3. And again, I still have the sine of x. And then I've got the x to the 6th, and if I reduce that by a factor of x squared, that's x to the 4th. And that's as simple as I can get that one.
So these don't really go out like all the way in, I guess. You know what I mean? Like keep going until.
Well, there's nothing else we really can do here.
Okay.
There just isn't anything else. The only thing that you could possibly potentially see doing is sort of breaking this into two fractions potentially. But there's really no reason to do it. It doesn't make it any better or worse than what we've begun with, so we don't need to.
I tried to do that on the homework a lot. Kept
Did
it
you?
wrong. Yeah,
I'm sorry.
it's okay.
We have 4 more trig functions that we have not yet discussed what their derivatives are, but we will now. I told you my favorite ones were already sine and cosine. Everything else is a little bit harder to remember because sine and cosine are just so friendly. Okay? So you guys ready?
Yes, ma'am.
Okay, these are in pairs on purpose, and you'll see them as we go. Why? So tangent. The derivative of tangent is secant squared.
Oh, yes. Good old days.
And the derivative of cotangent is negative cosecant squared. I'm going to tell you some devices on how to remember these. So we'll just write them in for now. Tangent is secant, and there's no mnemonics, but there's some patterns that are nice that help to keep the negatives in the right places and those kinds of things. The derivative of secant is secant tangent. Now, I'm being so sort of sloppy as I'm saying them. You have to make sure that the angle x is with each of them. Secant means nothing if it doesn't have an angle with it. It's like saying square root. And you'd be asking me, well, square root of what? Okay? Secant of x. And then the derivative of cosecant is negative cosecant x. Cotangent of x.
How come the cosecant is negative? Because
That's how it works out. I mean, like that's actually the right value. I want to show you something. I'm going to write the sine and cosine one in here just so you can see these two because there is a nice pattern in a few of these things. Okay, so these are in pairs on purpose. One thing you'll notice is that sine and cosine are very similar, right? Sine turns into cosine turns into sine. Tangent and cotangent turn into the other two functions that we haven't dealt with so far, squared. So that's kind of similar. Secant and cosecant have themselves in their derivative. Secant has a secant in it, tangent has a tangent in it. You never see a function and a cofunction together. So, right, you don't see secant cotangent, right? So if there's one that's a co, the other one's a co as well. Okay, same thing up here. Cotangent is cosecant squared. Notice which ones are negatives. Which ones gave you a negative derivative? All the cofunctions, right? Cosine, cotangent, cosecant all became negative.
Yeah, on the,
Oh, I left my negative off on sine. I was moving too quickly. Thank you. Let's get that in there. How about that? Okay, so all of the cofunctions are the ones that become negative. Okay, you're going to need to memorize these, as well as the product rule, the quotient rule, and the chain rule, which is our next one, next class period, for the test, okay? For the quiz that we're talking about, this gateway thing that's happening next week. You will need to memorize all these, okay? So make sure that you have done that. We're going to practice them, though, first. Y'all ready? Okay. Find the derivative of the function. Now, 1 over x, you can use, if you really, really want to, the quotient rule. I would never use the quotient rule for 1 over x personally, because I don't need to. How could I rewrite it so that I don't have to use the quotient rule? Yeah, x to the negative 1. So that's what I would do first. If you use a quotient rule, you get the same answer. It won't hurt anything. It's just a few more steps, and it's a little bit awkward because you're going to have some zeros in it because the derivative of the numerator is just 0. So it's kind of an odd one to use with that. All right, so what would the derivative of x to the negative 1 be? Good. Negative x to the negative 2. All right, we have negative 12 secant. Well, the negative 12 stays because that's a coefficient. What's the derivative of secant?
Secant tangent.
Secant tangent. And again, be careful when you write it down. Don't really write down what I just said, secant tangent. Write down secant x, tangent x. There is one step of simplification that we need to do. Yeah. The original function started out with a 1 over x, no a negative exponent, so our answer needs to also have no negative exponents. So this would be negative 1 over x squared.
On the gateway, will we be expected to like rewrite it?
Definitely not.
So if we just go through
So we can just leave it like that.
Yeah, you can leave it like our first step on this problem on the gateway. In fact, I'd encourage you to so that you don't accidentally make a mistake in case you're moving quickly or something.
Or I was just wondering, like, do we have to show that we rewrote it?
Nope, you don't have to. Yes.
I was kind of asking about the simplification because there was a problem down in the quiz where there was like a square root. And
Yes.
it ended up in the denominator, and I wasn't sure if there's a way to write that to put it in the numerator because the original one wasn't in the numerator.
There isn't because you'd have to have a negative, and we don't do negative radicals.
Okay.
So yes.
So you can just leave it.
Yeah, radicals are always have a positive. No, you can't leave it a negative exponent. You just need to move it to the denominator. I actually sent you an email this morning, but I didn't get your message until this morning. So yeah. Yeah, so if you have something with a radical in it, the only way to express the radical, if you've got a negative exponent, is to pull it down to the denominator and then put the radical in the denominator. Okay, let's try another one. Sine, cosine. All right, so tell me what you see when you see this problem. A product rule.
Okay.
Please, see a product rule, right? Now, we didn't do a product rule today. We did that last class period, so let's see if we can remember what we do for a product rule. What do we do first? All right, yeah. We write one of them down. I usually write the first one down, sine x. Next thing is I need the derivative of the second piece. So what is the derivative of cosine? Negative sine. Plus. Now I need the derivative of sine, which is cosine. And then I need the original of the second piece, which is another cosine. Okay, again, on the gateway, you would stop there. But there's got to be a better way to write it than that. It's a little bit messy. The first thing is I can pull the negative to the front. How else can I write sine times sine?
Sine x squared.
Sine x squared. Now, we do need to be careful where we put the squared. The squared goes here, and I know you guys probably have seen that before, but just a reminder. If you put the squared after the x, it means that the x is what's squared. If you put the square by the sign, it means that the sine of x, all of it, is actually squared. So it's a notational issue to try to clarify between those two options. Yeah, and if you put it in the calculator, that's a very true point. You have to use parentheses like this and the squared on the outside. That's true. All right, the other piece down here, cosine of x times cosine of x, then has the same feature. You would do cosine squared of x. Now, this didn't happen to be this way, but let's suppose for a moment that this had come out as sine squared x plus cosine squared x. What would happen then? You'd get the number 1, right? Okay, so there are really only 3 sets of identities that I expect you to be able to use at any given point. Reciprocal identities, quotient identities, and Pythagorean identities. If you're not comfortable or you're not sure or you don't remember what I'm referring to, there's a printout you can do from Moodle. It says trig identities, and it's the first 3 sets. There's more after that. We just don't use them regularly enough that I'm going to expect that you remember them all the time. But those 3 sets you should remember, and they will help you as you're working through some of these as well. All right, one more. Does this look like this on your paper?
Uh-huh.
Okay, the numerator looks like this?
Yeah.
Okay, I made a change at some point, and so I wanted to make sure it showed up on yours. All right, so this says to find the derivative. I do have a quotient rule here, right? So we're going to use the quotient rule. The quotient rule says, what do I do first? I write the denominator down. That's tangent of x. And then I need the derivative of the numerator. So what's the derivative of 2 minus 3x?
3.
Negative 3. Make sure you got the negative.
Yes, ma'am.
And then we have minus. And now I need the numerator, 2 minus 3x, times the derivative of the denominator. So what is the derivative of tangent? Secant squared. And then this is supposed to be written over the denominator squared. So what would the denominator squared be? Tangent squared of x. It's kind of messy on the numerator still. We'll clean it up. We're not going to do too much like trying to simplify trig involved in this problem because the question at that point becomes, where do I stop? You guys remember that from trig, right? Like, where do I stop? I mean, like I can keep doing things with trig because there are all kinds of trig identities I could keep sort of employing. At what point do I stop? So let's just clean up what we have with multiplying things out. Negative 3 tangent of x. And then over here, I've got a negative that's got to go through, and I've got a secant that's got to go through. So my signs are going to switch, and I'm going to be multiplying by tangent. So instead of having a 2, I'm going to have a negative 2, and then secant squared. And then instead of having a negative 3x, I'm going to have a positive 3x secant squared. And all of this is over the tangent squared of x. And we really are going to just stop right there. Could we make it look a little bit prettier with sines and cosines? Maybe. But it also may just make it look worse. That sometimes happens, right? We could potentially use a Pythagorean identity. There is a Pythagorean identity that involves tangent squared and secant squared. But it still has the potential for making the denominator even worse than it already is. There's just nothing that's for sure going to clean this up anymore. So we're going to leave it. Last question. All right, so we've got 3 times 1 minus sine of x over 2 cosine of x. This isn't a super big issue, but my suggestion when you see something like this is to just simplify what the numerator is. Just multiply the 3 through. Don't leave it in a form that's just slightly more complicated to make more of a complicated mess for yourself later. Just clean it up a little bit before you start. So I would have 3 minus 3 sine x. Over the 2 cosine of x. Okay, so we're going to start with the denominator written down, right? The denominator is 2 cosine of x. Sorry, my pen is not cooperating very well at some reason at this point. And then I need the derivative of the numerator. So what's the derivative of 3 minus 3 sine x? Negative 3 cosine x. So the first 3 is 0. That's its derivative. And then the derivative of sine is cosine. So the reason it's negative is because it's already got a negative 3 in front of it. It didn't change. It stayed the same. Minus. Now I need the numerator, which is 3 minus 3 sine of x, times the derivative of the denominator. So what's the derivative of 2 cosine x? Negative 2 sine x. So that one does change because it's taking the derivative of cosine. And all of this would be over 2 cosine of x, all of that squared. So again, be careful. That means the 2 is going to be squared as well, not just the cosine. So I will rewrite it, but I'm writing it like that on purpose for the moment. All right, so now I've got, if I simplify, negative 6 cosine squared of x. Man, I've got so many negatives in the second set. I'm going to cancel this one and this one, okay? Because I have to distribute both of them through, and they're both negative. So all my signs of the 3 and the negative 3 sign will stay the same. So I've now got a positive, but I have to distribute the 2 sine x to each of these terms. So what is 2 sine x times 3? 6 sine of x. And then I've got the negative 3 sine x times the 2 sine x, which gives me negative 6 sine squared of x. And then this is over, like we mentioned, 4 cosine squared of x. There is a very simple simplification on top that I would expect you to see at this point. Bryson's nodding his head. Do you see it, Bryson? Yeah, we mentioned this one before. I've got the sine squared, I've got the cosine squared, and they have the same coefficient, right? Negative 6. So if I were to sort of group those together and pull the negative 6 out in front, I'd have sine squared plus cosine squared. I'm going to actually write that out just in case some of you are nodding, but I'm not sure if everyone sees it for sure. So I'm going to write it that way. If you don't need to see this written, don't write it. That's fine. And then this other piece that's plus 6 sine x, I don't have to involve him in this substitution. There's nothing that I need to do with him. So I'm just going to write him out there separately. The part that's currently now in parentheses is equal to what? It's equal to 1. So I end up having this negative 6 times 1 plus 6 sine of x over 4 cosine x. And there's one more thing I can do. Do you see it? Yeah, everything has an even coefficient, right? 6, 6, and 4. So I can divide them all by 2. So I will simplify by dividing each of these by 2. So this will give me negative 3 plus 3 sine x over 2 cosine squared of x. Any question on that one? All righty.